So just to recap on what we were doing last time, so we started off looking at basically what quantum computers are on a sort of abstract level. So it's basically a multiple many particle qubit system where we've got, say, big N number of qubits here, and each of them, they're qubits, so they're all two-level states. So there's a total of 2 to the power of n different combinations. And so we can write a general quantum state as some superposition of those 2 to the power of n combinations. We can write this in a couple of different ways. So this is sort of the binary representation, or we could enumerate them by a number just from 0 to 2 to the power of n minus 1. Just labels them. And then we could write the wave function like this. This is just different ways of writing it, basically the same information. And when you have a quantum algorithm, what you do is to basically you have an algorithm which is a unitary evolution, because basically in quantum mechanics, any kind of time-dependent process should be described as a unitary evolution. So basically you've got your input state, and then there's some kind of unitary evolution, which is going to be, in this context, some kind of algorithm, and then there's a final state. But in order for us to get this information, we also have to perform a measurement. So when you perform a measurement, you'll get a bunch of different outcomes which are random according to whatever this wave function is. So the differences to classical computing is, firstly, well, of course, we don't have any superpositions in classical computing. We only got the binary combinations. So basically, classically, these ones are, going to be like all 0 except for 1, where one of these coefficients is 1. But in the quantum case, you can have any superposition. So that's one difference. In the classical case, the computation is by some kind of digital logic. Now we can, this is extended to this unitary evolution in general. So of course you can end up with a superposition here. And also, this measurement thing, we don't really think about so much in classical computing, because you take it for granted that you can always just read out whatever this thing here is. But in fact, actually, this measurement is just in the quantum case, you will really have this randomness in the measurement. So we have to think about that as well. Okay, so in general, we have this big complicated unitary matrix in principle. There's a lot of different matrices that you can have, because the only restriction is that this thing is unitary, and there's actually that family of matrices is big. Well, it's infinitely big. So it's so big that it's sort of hard to even think about. So we can do something which is sort of inspired from what we do from classical computing, and at this kind of basic digital logic level, what we think about is like a sequence of gates. And gates are a kind of nice way to think about things, because it's kind of quite compatible with how people think, right? So an algorithm is usually some kind of recipe, some procedure that you go through step by step, and it's like you do this, and then you do that, and then you do this, and then you do that, and then eventually you accomplish the task that you want. So you break it down into certain smaller tasks, and then we know how to do the big task by joining together smaller tasks. And so a sequence of steps is quite a natural way to think about how to build classical algorithms. And so quantum algorithms are kind of the same. You know, we can kind of think of it in a certain sequence where we perform particular steps, and then eventually we approach the problem, you know, step by step. So this is why, you know, having gates is a kind of a pretty natural concept. You know, these are sort of step by step steps to, operations in order to eventually achieve the algorithm or task that you really wanted. So digital logic has various types of gates. Now, the most commonly used ones are things like AND gates, OR gates, NOT gates, and there's a famous result in digital logic to say that you can make any gate out of a NAND gate. It's a NOT AND gate. And the similar result here is that you can create any unitary matrix just by combining 1 and 2 qubit gates. Okay, and it's a little bit different in the quantum case because, well, the quantum case is a little bit more general, and so actually it's it's a generalization of the classical case, and so the gates also need to be a bit different. You need a little bit more than just like one gate, but people have shown that with this combination of 1 and 2 qubit gates, basically this means gates that are involving only 1 or two of these, this is enough to produce. You can combine these things to produce an arbitrary unitary operation. Okay, so we sort of, the way that I'm approaching this is to sort of first look at the classical case and then see if we can translate that to the quantum case, and then see what the sort of what the differences are, and also what's allowed and what's not allowed. So in the classical computing case, there are the binary, the one bit of information is only 0 or 1. So actually, there's only 2 different states, and actually there's only 4 different functions in total. These are the 4 different functions or gates, if you like. So you can either have something that does nothing, or there's a NOT gate, which just flips it, reset to 0, which is to make 0 no matter what the input is, and reset to 1 is make 1 no matter what the input is. And we can make quantum versions of the first 2 because the kind of thing that we want to do here is to basically just transfer the input state to the output state, and the identity matrix is exactly what that does. The NOT gate, this is exactly what, the matrix would be to flip the input. And so this thing is a valid quantum gate. But these ones at the bottom are not, because they are not unitary operations. And the key thing about unitary operations is that they must be reversible. So in other words, this matrix must have an inverse. And because these matrices do not have an inverse, so that means that it's impossible to make them in quantum mechanics, because in quantum mechanics, everything is always reversible. Everything is always a unitary matrix. And so you just cannot implement this with a unitary evolution. So we don't consider these ones as gates. Yeah, okay, so, but actually there are a few more types of gates. So for example, this Z gate is another example of a gate. In fact, also the Y gate. So remember, we've been talking about this X gate, Y gate, Z gate. These 3 are all, valid gates because they're all unitary operations. But actually there's still more, not just X, Y, Z. There's also things like Hadamard gate, which is a common type of gate that a lot of algorithms use because basically this thing is unitary, but it is the gate that kind of produces this even superposition state. So you start with just the state 0, and it makes this like even superposition of 0 and 1. And that's kind of quite a useful step to sort of have in quantum computing. Okay, and actually, so the most general 1-qubit gate is, it looks like this. It's you have this. You can view this part of the evolution as some kind of Hamiltonian. So remember we talked about how in the Schrödinger equation the Schrödinger equation can be written as something like this. So this is our initial state, and basically this evolves to a new state at time t according to that. So this is obviously of Schrödinger form. So if we just sort of say that the Hamiltonian is, in this case, it's going to be something like, something like h bar phi over 2 of nx and y and nz. So basically by having a particular Hamiltonian of that form, then you can make this type of unitary evolution. And basically what this is that these coefficients here are just, this is like some unit vector, and this actually specifies the axis of rotation around which the state will evolve. And so if this is at some funny angle, then this would all these three things would be non-zero, and there'll be a rotation around that. This phi angle is the angle that it rotates around. So if you wanted to rotate, for example, a state by 45 degrees, then this angle, would be pi over 4 and so forth. I think this is where we got up to. Maybe what might be nice is just to give a little explicit example of this one. So let me maybe just go to the whiteboard and so just demonstrate this. Okay, so let's look at this particular case. So let's say our initial state is the state what we're often calling plus, and plus is the state which is a superposition 0 plus 1. And what we're going to do, and let's try to visualize everything on the block sphere here. So this is the z direction. This is, say, the x direction. And this way would be the y direction. And so our initial state is over here. Okay. And suppose we want to rotate this so that it's going to go to the state the z direction pointing in the positive direction. So what do you think, what axis rotation should we do in order to achieve that? So if we wanted to go like from here to here, so this is the final step. So what axis should we rotate around?
Be around y-axis and rotate pi over 2.
Exactly. Yes. Yes. Great. Okay. So according to what we've been told, I think this should have a minus sign from memory. Well, okay, we're going to find out. I feel like actually there should be a minus sign now that think of it. Okay, so let's go with the minus sign because I think that's what I remember from memory. Okay, so it should be the y-axis, as you correctly said there. So this matrix here is going to be y. So in terms of that unit vector, it's going to have to be equal to nx equals 0, ny equals 1, and nz equals 0. Sorry. Yeah, so that's still a unit vector. Of course, it's just pointing purely in the y direction. So this is our axis that we're going to rotate around. Okay, so and the angle should be pi over 4. Well, okay, so I guess it really depends upon which direction you take as positive, right? Okay, so I'm not completely confident about the sign, but all right, we're going to find out. So let's work this thing out. So remember that previously we did an expansion of this kind of Euler form, and we can work out that it's going to be something like this. So y, okay, an identity matrix here, because the y matrix, this y looks like this, minus I, and actually y squared also gives identity, okay? All right, so then a matrix is going to look like, so this thing here is 1 over root 2. This thing here is 1 over root 2. Okay, and then if you multiply y matrix by minus I, then, okay, well, let's do it step by step, not to get ahead of ourselves. So 1, 1, so this is identity matrix. And okay, minus I times by this matrix will give minus 1 and plus 1 here. Okay, and this will be 1 over root 2. Okay, so this is 1 over root 2, 1, minus 1, 1, 1. Okay, all right. Okay, so now I'm starting to see what's going to happen. And indeed, actually, so I've got the signs wrong. So, well, anyway, let's just complete the calculation. So, all right, so if we now, what we're going to do is we're going to multiply, this matrix, and we're going to multiply by the matrix that we have here. We're going to multiply this matrix by the original vector. And so what this is going to be is 1 over root 2, I shouldn't say equals 2, but the rotation times the state will give 1, minus 1, 1, 1, 1 over root 2, 1, 1, right? And if you do this, then this will be a half times by 0, and 2, and 0, 1. Okay, so as I said, I wasn't confident on the sign, and in fact, what we've just achieved is we've gone around the wrong way. We've ended up down here. So we can easily fix that by just changing the sign of this one, change the sign of this, which changes the sign of that one, which will change the sign of this one, which will turn this one positive, this one negative. Okay, and then this one should be negative. And then how this changes things is that the top one will be 2 and 0. And okay, and then this is what we wanted, because the north pole on the block sphere is the top state, which is the zero logical state. Okay, so this was just sort of a simple example just to show that how this rotates. Now, if you were to do something more complicated, so if you had some weird angle that you're rotating around, so it's not X, Y, or Z, maybe some like weird angle, some funny angle like this, then the way that you would work it out actually would be very similar. So just, I'll just show you just generally how it works. But the thing about, so if you've got, so let me write that. So if you've got n dot sigma, and this is the nx x plus ny y plus nz z. Okay, so this thing you can write in terms of the sine and the cosine in just exactly the same way as we've been doing for the other Pauli matrices, because actually you can work out that n dot sigma, say, squared is actually also equal to identity. So, you know, you can do a little bit of maths to work that out, but basically it happens because when you do the square of this thing, all the terms like x times y, they happen in pairs, like x plus y, sorry, not x plus y, but x times y plus y times x. Actually, you can work out that all such terms are equal to 0, and then you only get the diagonal terms, and then eventually you'll get something like nx squared plus ny squared plus nz squared, and that's equal to 1. So basically, you can work out even something at a funny angle like this, because this thing will be equal to cosine of 5/2 plus I sine 5/2 n dot sigma. Okay, so I didn't have this in the slides, but that's just for your information if you ever need to calculate anything like that. Okay, is this all okay? Okay, hope so. Okay, so let's just go back to slides. Okay, so yeah, so we can, this is the most general 1 qubit gate that you can actually make. And yeah, so the ones which I was talking about here are actually just some kind of specific examples of this. And the most, the most general 1 qubit gate can be written in this form. Okay, so now let's go on to 2 qubit gates. So let's sort of do the same kind of strategy as before, where we sort of start with the classical versions and sort of try and generalize it. Okay, so let's look at like some common 2-bit gates, so classical gates. So we've got like the AND gate, and I think as I did before, and we have, 1 only when there's like both inputs are 1. The OR gate looks like this. So the output is 1 if any time you got a 1 on the input, then the output will be 1. NAND gate is like the AND gate, but then you flip the output of this. So wherever you have zeros, you have 1s. And exclusive OR is, so, when you say something or something, like in English, it's a little bit ambiguous whether it means, you must have only 1 thing satisfying it. So, language is not exact, right? So just to give the example that I gave the other week, other lecture, I mean, so, if I'm saying I'm going to the beach, if it's sunny and it's Wednesday, okay, so, if it's sunny, then I'm going. If it's Wednesday, I'm also going. But what if it's sunny and it's Wednesday? Presumably you are still going to the beach, but it's kind of, it's not completely clear whether it means that you're still going to go to the beach. I mean, it makes a lot of sense if you do go to the beach in that case, but you know, it's a little bit ambiguous. And so exclusive OR is actually like OR, except that if both conditions are satisfied, actually you don't go to the beach for some weird reason. This one is 0. Okay, so let's just look at these gates and firstly see if we can make like a unitary version of these gates. Now, immediately there's a kind of a problem. Can anybody sort of spot what the problem here is?
I'm sorry, Professor. What is X? Like XOR? What is the X?
Well, X stands for exclusive OR. So it just means it's exclusive, meaning like strictly OR. So, you know, I'm going to the beach if it's Wednesday or it's sunny, but I'm not going to go to the beach if it's Wednesday and it's sunny. Okay, so you know, you really need it to be OR in the sense that it must be only one of those and not both. That's basically what exclusive OR means. But you know, that's just a definition, and you don't really have to worry about exclusive ORs or regular ORs or anything like that. But you know, what I want to try to get you guys to think about is, so if we were to make a quantum version of these gates, there's an immediate problem here. So what would be the problem? Or, you know, what do you think is the obvious problem here? Maybe not obvious, but what do you think is the problem here? If you were to make like the quantum versions of these ones?
Like the input, is it a composite state, but the output is just one state?
Right, yes. Yes, so yeah, exactly. So it's kind of impossible to make a reversible gate here, right? Because the input states, you know, there's 4 combinations, right? And the output, well, there's only going to be ever 2, right? It's only ever going to be 0 and 1. Now, if there's only ever 2 possibilities, and imagine you're here on the output, and basically reversible means, okay, you know, just by looking at whatever the output is, you have to be able to figure out what happened on the input. Now, it's an impossible task, right? Because there's 4 different input combinations, but then there's only 1 output. And so how are you ever going to get like, you know, figure out what these 4 combinations are just with like just a 0 or 1? You know, there's only 2 different possible outputs. So it's kind of impossible. It doesn't really matter even what these combinations, like what these gates even look like. It's a kind of an impossible task because it's there's not enough, you know, combinations of outputs to figure out what the input is, right? So you know, it's you know, looking at the classical setup, it's already immediately obvious that it's not reversible. None of these gates are reversible. So we're going to have to tweak it a little bit, and so we're gonna make this tweak so that it's at least, you know, in principle possible for these gates to be reversible. And the tweak that we're going to do is to add like an extra kind of a copy leg of like one of the inputs. Okay, so at least then we've got you know, 2 binary numbers as the outputs and 2 binary numbers as the inputs. Okay, so at least, you know, now it's going to be possible to try and figure it out, because you know, we've at least got the same number of variables on the input and the output side. So we're gonna sort of make that adjustment just to make it at least possible. Okay, so we're just going to copy like the first input. So it doesn't really matter whether it's the first or the second one actually. So we're just going to choose the first one just for just to be you know, for definiteness. So we're going to now have truth tables that look like this. So the output of the first one is just simply going to be the copy of this one. So here, all the numbers are just simply copies of the input 1. And basically, these are the, you know, the 2-bit outputs. These are basically what we're going to look at and to figure out whether we can make reversible gates out of these things. So let's start with the AND. So is this a reversible gate?
Like we can still we can array like 0, 0 to 0, 1 input because they both get output 0, 0.
Right, yes, exactly, yes. So yeah, so this is, you can't make this reversible because, yeah, like both of these cases give 0, 0, right? So if you're sitting here and you're just receiving this output, right? Now, how can you possibly tell whether it was this case or the second case? Because in either case, they're going to give 0, 0, right? So it's impossible that this is reversible because you're going to have both of these cases as 0, 0. So this is not a reversible gate. So actually, AND gate is we can't generalize this to the quantum case. All right, what about this one, the OR gate? Is this reversible?
No.
Yep, no, because
the last two both get 1, 1.
That's right. Yeah. So same reason now, but this time these ones are both 1, 1. And now, so you can't tell just by looking at the output what these guys are, right? And what about the NAND gate? This was the one that was in classical digital logic, going to give us a completely universal gate set. Now, this one, is this reversible?
No.
Again, no. Yeah. So again, the first two, yeah. So 0, 1, can't tell the difference between these two. Okay, so this is looking quite bad so far because none of our gates we can make quantum generalizations out of, right? Okay, what about XOR?
Yes, this can.
Yes, this one you can, because basically we can work out what sort of the rule would be, because so if it was 0, 0, then we know that the input was also 0, 0. If it's 0, 1, then the input was also 0, 1. But in this case, if it was 1, 1, then it means like the second one, the bit is the opposite of this one. And over here, well, you know, in one, copy is always going to be the same as this one, right? But these guys are actually kind of flipped, right? So this is a sort of yeah, so we can work out what the input is from just looking by output, because we can just say, well, okay, for these two combinations, just flip this one, and then we can figure out what input 2 is. So well, fortunately, we do have a 2-qubit gate that we can make a quantum state out of. So yeah, so these first 3, we just cannot make them reversible. So there's no way that we can make a unitary evolution out of them. So this is what we call, in the quantum context, the we don't call it XOR, we actually call it the C-NOT gate. And the C-NOT gate stands for controlled NOT. And what I was just trying to explain to you actually gives you a bit of a hint of why it's called controlled NOT, because basically, if you look at this truth table, so the first input is just the same, okay, so there's no difference. But the second input, basically the rule is that if you start here and figure out what's going on here, the rule is basically, if the first one is 0, then just do nothing to the second qubit, okay? But if the first one is 1, then flip it. So you go 0 to 1 or 1 to 0, okay? And so if you write this as a matrix, it looks like this. Basically, it's sort of like, it's block diagonal. It's the first block has a 2x2 identity. And the second block has, it's like this X gate, which is a flipping gate. Okay, so it flips the second spin. And the symbol for this looks like this. And this first one is what you call the control qubit, because this one you can think of as the one that controls what's going to happen to the second qubit. Like if this one is 0, then it's this one has nothing happen to it. But if this one is 1, then you flip it, right? So it's sort of like controlling what's gonna happen here, because you know, when you if this one is 0, then this one you do nothing. If this one is 1, then this one you flip. Okay. So this is a very important gate in quantum computing. You see it all the time. And if you're wondering, okay, you know, what we've been saying sounds almost pretty classical, right? Like if I'm saying, like, if it's 0, then do this. If it's 1, do that. But actually, doing this in the language of superpositions, it's basically no difference, because you can always make a superposition of these cases. So, you know, instead of saying, if it's 0, do this. If it's 1, do that. Basically, in the quantum language, what that could mean is that, you know, if it's a, like, so instead of if 0 or if 1, basically you can have a superposition of both 0 and 1. So it could be both in 0 and 1. And in the quantum mechanics case, it would act differently on different terms in the superposition. So what happens is that you have a general state here, and this is what our matrix looks like, this unitary matrix. And this is the general state. And so if you start with this general state, apply it to this matrix, then basically what this gate does is it kind of like flips these last two entries. So this is, of course, just a superposition state, and, you know, perfectly compatible with quantum mechanics. So this is, yeah, this is basically what it would do to the quantum state. Questions?
How do you understand those 0, 0, 0, 1, 0, 1, 0, 1, 1? Like
which one? Here? Here?
Yeah.
Yeah. So I'm just writing this one as a guide, because, you know, whenever you write a matrix, you know, like, you know, if I were to say that, okay, the X gate is this matrix, right? When I write a matrix, there's always an implicit kind of convention of what the ordering of the states are, right? So I just wrote that just to make it explicit what states I'm really talking about here. So so in the case of the X gate, if I were to just write the basis ordering convention explicitly, I would just write it like that, because that it's not like in the single qubit case. I think everybody just intuitively just realized it's the ordering is 0 and then 1. But then in this case, two qubit case, it might not be so as obvious to know what the convention of the ordering is, right? So I just wrote the convention, the ordering, and so just to make it a little bit even clearer, when I write this ABCD, well, okay, sorry, not there, but let's just write the initial state here, ABCD here. So if that state is like that, basically what I mean by that is just A 0 0, B 0 1, C 1 0, and D 1 1, right? And that's because the ordering of these states here, I've got the same ordering of the states as I've written up there. So yeah, so I hope that's clear.
Yes, I get it.
Okay. Any other questions? Okay, no, all right. Okay, so let's just do a little bit of a practice together. So suppose you start in this state, which is plus state and 0. And then you apply the C0 gate. Now work out what the final state there is. So I'll give you just a minute or two to work that out. Maybe I'll just put it on this slide so that you have the definitions there. So, okay, so I'll leave you to do that for a minute. So the state that we're going to work on is plus and 0, okay? Okay, how did you guys go? Anybody got any answers?
One or square root 2 times 0, 0, 0, 0, 0 plus 1, 1. The state.
Right, yeah. Okay, correct, yes. So, yeah, so you can do this a couple of different ways. So either you can use the like kind of a matrix method. In this case, so when you write plus and 0, then okay, so the first one is actually a superposition of 0 and 1. And then so the two states involved are the 0, 0 and 1, 0 state. And according to the convention of this matrix here, 0, 0 is the first one and 1, 0 is the third one. So basically we need a vector which has 1 in the first and third spots. So here and here. And then from there, we just do a matrix multiplication of what that matrix that I wrote is, and then it's like this. So you can do it like that, but maybe I think I would prefer the this bracket kind of method. And the way to sort of remember the C naught is, this diagram kind of gives you a lot of sort of hints on that. And basically the rule is that if the first one is 0, then do nothing to this one. The first one is 1, then flip it. Okay, so it's actually clear already that this should be the answer, because basically here's your gate here. It's being applied to this state, right? And just you look at basically the first one. That's the control qubit, right? The first one is the control qubit, and you say, okay, it's 0, so I'm going to do nothing to that one, right? But here it's 1. So I'm going to flip this one to 1, okay? And basically that's how you end up with that. So I think this is a lot shorter and simpler than the matrix method, which is, you got to write a lot of zeros and matrices and stuff like that. So you do it either way in principle, but I think this is the preferred method. Okay, any questions? I think that's the end of this slide set. Okay, no. All right, then let's go to the next set, which is quantum circuits. Okay, so yeah, well, maybe no need to really recap, but so we've met a bunch of different quantum gates, and because of this rule, or not rule, but this result that people have discovered, that you can make any unitary out of just 1 and 2 qubit gates. So actually, all the combinations of we can make quantum algorithms just by combining gates that are like this the gates like this. Actually, there's maybe a few more gates we need, but for the 1 qubit gates, so in order to have a completely universal set, I think you need a couple more one qubit gates. But another way to sort of say the same result is that if you have the most general 1 qubit rotation, the one that we had, like this one that was I5/2 and sigma, this one. So if you have this one and this one, then yeah, definitely it's completely universal. So you can make any unitary rotation just from the combination of this one and this one. Or what you can have is these gates like Z, X, this Hadamard, I think you also need another gate, like I think it's called the T gate, and I think it's got some kind of phase like this. I think I'd need to look up exactly the gate set, but you can make also another, if you really want to minimize the number of different gates, then you could also do it like that as well. But anyway, the point is still, it's always like 1 and 2 qubit gates. Okay, so so what we're going to do is to look a little bit more into quantum circuits, okay? And what I already kind of had it already in the last gate set is that you can, you basically always, in a quantum circuit, you tend to always have some input state, and then there's an algorithm part of it, and then there's like the final state, and then there's the measurement state, okay? Now, actually, we're going to sort of even simplify that a little bit more. And in fact, we can always write it. Previously, I always said that like you have some input state, right? But actually, I'm going to even simplify it even more by saying that actually the input state can always just be 0. And this part of it is basically the same, except that I didn't really write it exactly like before. I just have this measurement device, which I just have a simpler notation for it over here. This is the more common notation. In fact, you just show like a meter to imply that this is a measurement. And this will, each one of these ones will randomly give, 0 or 1 according to the quantum mechanical probabilities. And basically, this covers, just about every quantum algorithm that's basically known. There are some other complicated algorithms where you can, base something based on these measurement results. You again do something back to the algorithm. So I'm not really going to talk about those ones so much. So we're just going to stick to this class of quantum algorithms, but this is already pretty general, and you can do a lot of things with this. Okay, but firstly, you might be sort of a bit puzzled to hear rather, why did I just limit the input state just to 0? This definitely looks like a, not as general as what I was saying before, where I start with any input state, but now I'm saying the input state is always 0. Okay, so what's the deal with that? Well, okay, sorry, I've got ahead of myself, but okay, let me just, okay, sorry, I'll come back to that point. Sorry, I forgot that I was going to talk about this kind of stuff. Okay, so I'll come back to that point about why the initial state doesn't have to be 0. Okay, but basically, yeah, so a quantum circuit will typically look something like this. So, inside this algorithm will be some combination of different gates. So this is just some random circuit, which I sort of just made up. It doesn't really do anything very useful, but, might be a particular type of quantum algorithm. So here's a bunch of gates that are happening on each qubit, and then here are the controlled NOT gates. Now notice that sometimes these controlled NOT gates can be like sort of far away. They don't have to be just right next to each other. And just in terms of the notation, only the qubits that have the dots here, right? So this black dot is controlling the output of this qubit here. These ones where it just crosses, nothing happens to it. Okay, so these ones, there's nothing that interacts with them. It's just it's just crossing. Only the things with the dots actually really do anything. So basically, by having this sequence, and the time sort of goes from left to right here, just like in digital logic circuits. So you basically start the state here, and then the first thing that you do is you apply this Z gate to this first qubit, and then also the C naught to the second and third in this circuit. Then you apply X and Z and so forth. It doesn't really matter what order you apply these two, because they happen on different qubits. So even if you did actually this one first and then this one second, or this one second and this one first, it wouldn't really, it doesn't change the output of the algorithm at all, because basically these qubits that are involved, they're not related to each other. So any time you have gates that are not related to each other, it doesn't really matter what the ordering is. But things like, for example, the ordering of, for instance, like these two, this would matter which order you do it in. So you certainly do need to do this one before this one, otherwise you might get a different result. You, generally speaking, you perform this sequence of gates from left to right. And then once you've done your algorithm, you do your measurement, and then you read out the results. Okay. So yeah, so I think I said a couple of these things already, but basically, yeah. So when you write a quantum circuit like this, then you go always from left to right. This is kind of the convention. So the time sort of goes from left to right, if you like. You can think of this, you can always draw a line, imaginary line, and imagine like, the sequence of operations that are actually happening. Okay, so this is like your timeline, like in YouTube or something, right? This is your time scroll bar, and it's going from left to right. Yeah. And basically at each point in time, there would be some quantum state. It would, initially the quantum state is this 0, 0, 0, but it's changing, at this point, the state will be something else, right? Well, actually, according to this circuit, it wouldn't be different, but okay, at this point, it would be something else apart from 0, 0, 0, be a new state, and so forth. So you keep on going across here, and then there will be a different state at each point in time in the circuit. Second sort of thing is that these horizontal wires, these black lines, if there's nothing there, basically nothing really happens. And so you can kind of think of this as just being an identity matrix. So whenever there's no gate here, there's basically no operation on it. In other words, you can just have an identity matrix for that step. Some other rules are like, there are no kind of loops like this, because this doesn't really make sense in the quantum circuit sense, because I wouldn't even know what this kind of means in a quantum mechanical language. I mean, here, okay, so some gate applied to it, but then here you can't really have these things sort of traveling backwards in time, because basically going left to right is kind of the time evolution. So if you've got something which is moving right to left, then this is sort of traveling backwards in time, and well, we're not doing time travel, so there's no backwards in time kind of evolution. So this doesn't really happen. Also, you can't really split the things into two qubits as we did do actually in classical, in classical circuits. So remember, we did, certain things like, so when we were doing that AND gate, in order to have an extra input, we just split it here, and then we had two outputs, right? So, in classical logic, this is possible because it's always possible to just copy a state, right? So what this could mean here is that, whatever your state, whatever your input here is, if it's a 0, it could just mean that over here, I just copy whatever that is. So if it's 0 here, it's also 0 here. But actually, in quantum mechanics, we can't just copy these quantum states. In fact, I think we'll do a bit later, but there is actually a famous result called the no cloning theorem. And this actually says that it's impossible to just clone or copy qubits. So, it's impossible just to have psi as an input psi, and then that goes to two copies, 2 qubits for the same psi. This is only possible actually in the classical case and not in the quantum case. So this kind of fan out kind of thing is also not allowed in the quantum circuit, and neither is sort of, I don't know, joining these things together, because this would physically be 2 qubits, and we can't just all of a sudden lose 1 qubit. If they're physically 2 qubits, then these are 2 physical atoms. You can't just sort of just lose it and all of a sudden not have 2 qubits. So if you started with n qubits here, then you always have to have n qubits at the end. Okay. Right. So sorry, this was what I was about to explain, and then I forgot that I had a couple more slides before explaining this point. Okay, so previously I was saying that quantum circuit always sort of, you can start in some initial state, and then, there's an algorithm, and then you do a measurement, right? So why did I make that restriction to the initial state being 0? Surely this is not as general as starting in a general initial state, right? But the reason why we don't have to, we can actually just think of this kind of restricted case when the initial state is just 0, is that although we could start in some other state, and that's actually totally possible, we can actually always consider like a preparation unitary algorithm in order to prepare that state from this 0 state, because there's always some unitary matrix in order to prepare the state that you sort of wanted from 0. So there's always some unitary step that we can go from here to here. So in that sense, we can just always kind of combine these two into one big algorithm, and then just start with 0, 0 as the initial state. So in the end, basically, if we just consider the preparation step to be part of the algorithm, then we can just lump it all together and just say that that's our algorithm. Okay. Right. Okay. Yes. One pitfall that sometimes some people make is that because of the convention of this circuit here, so as I said, sort of time goes from left to right here, right? So this actually means that the things on the left are applied before the thing on the right. Okay. Actually, this is exactly the opposite notation to how you'd write it mathematically, because when you write it as a sequence of operators or matrices, actually the things, here's our state. The thing that gets applied first is this one, which is on the right, right? And then second, this one, UAlg, would be applied after that, right? So actually the order of writing these things in the quantum circuit notation is actually kind of the exact opposite of the mathematical notation. But okay, so this is one inconvenience that you just have to live with because, well, it's just sort of historical reasons. I mean, people in digital circuits somehow left to right is the most common way, and so because quantum circuits are kind of trying to follow this like notation of the digital logic circuits, which was this way, but then also because now quantum mechanics involves mathematics, and that is written sort of the opposite way, now we've got kind of two ways of writing it, and then exactly the opposite. And well, you just have to live with it. So, but just be careful that you get the ordering of these gates always correct. Okay. Okay. Another kind of restriction that you might think we've got here is that actually the measurement basis is always in the 0, 1 basis. Now, if you remember, actually, you know, when we did when we did measurements, remember our measurement box had some knob on it at the top, so we could change like the basis of the measurement, right? So, you know, this actually looks like another restriction, because if we're just only ever measuring in 0, 1 basis, you know, how come we don't ever think about measuring in, you know, plus minus basis or something like that? And actually, even this one, this is actually not really a restriction in the end, because what we can do actually is to apply another unitary just before this measurement. And if you add this unitary rotation in order to change the basis just before this measurement, we can actually think of this combined thing of just this purple unitary here, and then the measurement here, combine that together, and that is actually our more generalized measurement. So we can actually, we don't have to think of the measurement itself being in this different basis. We can just combine it with just the regular 0, 1 measurement, and then you know, apply a unitary just before we do that. So again, actually, we can combine this whole algorithm into, you know, if we wanted to measure in a different basis, we can combine the algorithm itself and this basis change part of it into one giant unitary, and then just call that the algorithm. And so, you know, if we combine all these things, then we can, well, view this as our algorithm. Okay, so, you know, why is it that this combining this unitary and the measurement actually changes the basis? So there's a little bit of maths to do it. Maybe, I think there's not really enough time to do it today, so maybe I think I'll do that next lecture. So let's leave that for then. Any questions on the stuff I've done today? Okay, no questions? Well, you can always ask me other times. So, all right, then we'll leave it there.
I actually come up with a question. Just
okay.
So,
yeah.
if the C naught gate, like if it is reversed, like if the dot is on the bottom and the knot is on the top, then so it's just this C naught matrix, just those two blocks just change their positions, like.
Yeah, so that's actually a different gate. So yeah, if you swap the you know, bottom and the top ones, then it does a different thing actually. So you know, this is actually kind of different to this one, right? And in terms of the matrix, yes, it's it would just be like, you know, 1 1 1 1, and also you can sort of see that it's going to give a different result, for example, here, because if instead of doing this one, but if we did this in this case, right, you can see that we're going to get a different answer because, for example, yeah, so if we did U C naught, but then actually the second is the control qubit. So maybe I'll specify it sort of like this. Then what's going to happen is that 0, 1. So, the easiest way to do this, as I said before, is to say, look at these terms here and look at what the action of the C naught is term by term. So this one is the control qubit, right? And then this one is the, normally call it the target qubit, okay? Now, because the control qubit is actually 0, then the C naught says, if the control qubit is 0, then do nothing. So actually, in this case, nothing will happen to the state. Okay, so it will remain in this state because the second qubit is 0. That's the control qubit, and then the target qubit is the first one, and then basically nothing will happen to it. So yeah, so it's definitely it's kind of quite a different gate to if you swap the ordering of it. Yeah. Any other questions? No? Okay. Then we'll leave it there. I feel like some people want to ask questions in a way, but anyway, if you have more questions, then just, you can always let me know by email or whatever as well. So, okay, then I think homework, some of you have already handed it in. Where are we up to in the homeworks? We're up to, was it 10? So this was...
Yeah, I think 10, yeah, 10 is the content of Tuesday.
Right, okay.
Yeah.
Okay, all right. Okay, so don't forget to hand in your homework if you haven't done so already. Okay, but otherwise, see you next week.
Thank you.
Okay. All right.
See you.
Good,
See you.
Bye.